dynamic efficiency is about efficiency across time. So how do we look at how valuable something is today as compared to what its worth is to us in the future or to somebody else in the future? We might decide to use up all the oil today, leaving none for future generations, for example. To begin with, as part of this calculation, we need to know how to calculate present value and future value. So I'm going to give you these equations. Make sure you write them down. You're going to be using them on exams, and you need to understand them. So they're basically the same formula with one minor change. Present value is equal to future value divided by 1 plus the interest rate, both to the power of the number of payments. So PV equals FV divided by, parentheses, 1 plus R, right parentheses, to the power of N. Now, future value is exactly the same formula, only it has a multiplication in. So future value equals present value times 1 plus R to the power of N. Now, how do we remember this? Well, we remember this because future value is always going to be bigger than present value because it's going to accumulate interest. So bigger times. Whereas present value is going to be smaller than future value because we're going to discount it. So future value divided by, okay? Easy to remember. So we need to use those equations. So what is the interest rate or discount rate? We talk about interest rates all the time, but why do we have interest rates and what do they consist of? So interest rates are a measure of a number of things. First, they are a measure of the inflation rate. In other words, if we're going to loan money to somebody and we know there's 2% inflation, we want to get back interest that's at least 2% or we're losing ground. Second, the interest rate is a measure of risk. How likely am I to be paid back? What would happen if you disappear? What happens if you become bankrupt and you never pay me? So I have to consider how risky of an investment I'm making and what kind of collateral I have. And then I would adjust the interest rate for that. Third, the interest rate reflects opportunity cost. What could I do with the money if I don't loan it to you? Maybe I would like to put in a pool, and that means a lot more to me than having some interest. Maybe I'd like to buy a house. Maybe I'd like to do something else with my money. And so the interest rate is a combination of inflation, risk, and opportunity cost. So when we're calculating dynamic efficiency, we have to look at the value of resources in the future, but we have to discount them to present value them because they have more value today than in the future. For example, we might decide, you know what, we should leave as much oil for the future generations as we consume. So we're going to use a lot less oil. Well, maybe that's not the best idea. Might be, but it might not be. Why? Because it might be that in the future, nobody wants to use oil and they consider it dirty and they have better alternatives. And so they give up on oil and they never use it. And so the fact that we saved some for them and have it in barrels for them to use doesn't really mean very much because they don't really want it. My father-in-law liked to collect things, and he had a large collection of stuff. And I remember he had an old rusty ice cream maker and with a little crank on the side. It was all rusted out. And he said, isn't this cool? This is great. We used this when I was a kid. I thought my kids would love to have this. And I said, well, let's see what it's worth. So I went on to eBay and I looked it up, and sure enough, I found one. Only the one I found wasn't rusty. It was basically in brand new condition. And it was for sale for $10. So is it worth keeping that on a shelf for 70 years in hopes that some future generation might enjoy it? When after 70 years, I can buy one for $10. What is the present value in 19 20 of a can that was only worth $10 in the future. A few cents, probably not worth the trouble. Remember that the definition of dynamic efficiency is maximizing the present value of net benefits across time periods. Maximizing the present value of net benefits across time periods. All right, so to begin with, what I'm going to do is give you a very simple model. In this model, we're going to have an equation that represents the utility of, let's say, oil in 2 time periods. And it's going to be based on a price. Let's say that both time periods have the same formula. P equals 8 minus 0.4 Q. So the first thing that we can do is set Q equal to 0. And if we do that, then the price is 8. What that tells us is that at $8, I don't want any oil. I have no interest in oil at all. Now let's set the price to 0. And it turns out that the 0 price that we solve for Q, it equals 20. Okay, so let's introduce the dynamic efficiency formula that you can use to solve problems on your midterm, but also that you can use in the future. In this model, we use utility as based on a price. It's really the only method that we currently have for determining utility is what people are willing to pay. So in this particular case, our price is equal to a function, 8 minus 0.4 times the quantity. Now we have 2 time periods, period 1 and period 2. And we're going to keep it very simple and say that both time periods have the same utility function. So we can then say 8 minus 0.04 Q1, that's time period 1, is equal to 8 minus 0.04 Q2, which is time period 2. Now remember that the available quantity that we have to share is 20. Therefore, if we consume all 20 units across the 2 time periods, Q1 plus Q2 equals 20. We then take that equation, Q1 plus Q2 equals 20, and we determine that the interest or discount rate is going to be, in this case, 6%. And what we want to do is use this as part of a present value calculation. So present value, that's on the left, and future value on the right, okay, here. And then we divide that by 1.06 to the nth power. Well, to keep it simple, we'll make n 1 year. So that makes it 8 minus 0.4 Q1 equals 8 minus 0.4 Q2 divided by 1.06 to the 1 power, which is 1.06. 8 minus 0.4 Q1 equals 7.5472 minus 0.37736 times Q2. Now let's bring that equation to the next page. Okay, up here at the top. And let's simplify further. So the first thing that we can do is subtract 8 from both sides. And we get minus 0.4 Q1 equals minus 0.4528 minus 0.37736 Q2. Now, because all of them have negative signs, we can convert them all to positives. That makes it easier to work with. 0.4 Q1 equals 0.4528 plus 0.37736 Q2. Now let's isolate the Q1. We do that by dividing both sides by 0.4. So that makes this 0.4 divided by 0.4 is 1. So this becomes Q1 equals, and then it's 1.132 plus 0.9434 Q2. Now, remember that Q1 plus Q2 equals 20. Well, there's Q1, and we know Q2 is right here. So we can simply plug this equation in for Q1, and we get 1.132 plus 0.9434 Q2 plus Q2 equals 20. Now, there's 2 things that we can do with this. First, we can combine these two Q2s. So remember, this Q2 is a 1 Q2, and this is a 0.9434 Q2. So that becomes 1.9134 Q2. And then we can subtract this 1.132 from the 20, and we get 18.868. So what can we do with that then? Divide both sides by the 1.9134, and we have Q2. Q2 equals 18.868 divided by 1.9134, which is equal to 9.856, and that is the answer for Q2. To get Q1 is very simple. We know that Q1 plus Q2 equals 20, so Q1 is equal to 20 minus Q2, or 10.144. We now know that the optimal consumption of oil in this case is for the current period to consume 10.144 units, and the future unit consumption would be 9.856. So this is the dynamic efficiency calculation. I've given you the formula, so you need to write notes, write down notes. I will be sending you out an extra credit problem opportunity on this through email. And imagine that something like this is going to be on the midterm, which is coming up next week, or when you see this week.